All right. Welcome back to the interactive sessions of the course Viscous Fluid Flow. We begin by having a quick recap of what we saw in the previous week. So in last week, we basically looked at the boundary layer theory. So we basically started the boundary layer theory by solving a rather simple problem, which was basically based on the fact that there is a flow uh, having a magnitude of u infinity at far field, and it just moves over a flat plate. Uh, so the question stated that the velocity profile was given by a parabolic function whose constants a, b, and c were not known. So the first task, what we need to do was to solve for these constants a, b, and c by using the appropriate boundary condition at the far field and at the point where the fluid layer just is in touch with the plate, that is at y equal to 0. So we evaluated the constants a, b, and c by applying boundary condition at y equal to 0 and at y equal to delta. So as you can see, there are three unknowns. Since it's a parabolic profile, we require three boundary condition. So we applied the no slip boundary condition here. We evaluated basically the constant a by applying that no slip boundary condition. Then we said that at y equal to delta, that is at a distance when my coordinate is approximately equal to the boundary layer thickness, my velocity u is u infinity. And using the fact that at the intersection of the inviscid and the viscous regions, the shear stress basically diminishes to 0. And using this, we evaluated the constants A, B, and C. And once we are done evaluating the constant, our next task was to evaluate the boundary layer thickness delta by using the velocity profile that we saw by evaluating the constants A, B, and C. So for that, we use something which is known as the momentum integral equation for a flat plate. And for a flat plate, the integral equation basically reduces to this form, which says that the wall shear stress divided by the flow kinetic energy is equal to the rate of change of the momentum thickness. Sorry, it's not the rate. It's the change of the momentum thickness along the x direction. It's not the rate. Sorry. Nonetheless, this was basically the momentum integral equation that we saw, and we use this to evaluate how the boundary layer thickness delta varied with x. For that, we use the definition of momentum thickness, which is basically integral 0 to delta. It is u by u infinity times 1 minus u by u infinity. And then once we know u by infinity from the second order profile that we already evaluated, which is this, we evaluated how this delta essentially varies along x, and we found out that by choosing a second order velocity profile or by choosing a parabolic velocity profile, which you know which satisfies the boundary condition at the far field and at the point where the fluid layer is in contact with the plate, that is at y equal to 0, by choosing that velocity profile, we saw that delta by x essentially varied as 5.48 by square root of rex. So we ended by saying that if we compare this now with the exact solution derived by Blasius using the similarity profile or using the similarity analysis or the similarity principle, the constant that Blasius evaluated is basically 5. So it's a way of saying that the momentum integral approach essentially works if we basically compare how the constants 5.48 is close to 5 basically. So the momentum integral approach is simple and yet powerful, because once we know how the velocity profile essentially varies, so once we know the form of u by u infinity, this is sufficient for us to know how delta basically varies as x. So that's what we saw in the last class, and we concluded with that. This is a respite because of the fact that we need not always need to follow the Blasius solution. Typically, because sometimes the Blasius solution is not very straightforward to uh, you can say to calculate, basically because we need to start off with the governing differential equation of boundary layer theory in a flat plate, then substitute the velocities in terms of the stream function, and then you need to solve basically an ODE which is non-linear and it's of third order. So an analytical approach to that problem is not is not so trivial, and that's why like the Blasius solution, even if it's an exact solution, uh, has its own merits and demerits. That's basically the key takeaway. So today we will proceed with the boundary layer theory, and we will look into some other problems involved with this laminar boundary layer. And before starting off with the problems, uh, so I would again wait here for some more time. If you have any doubts related to the assignments or like anything pertaining to the previous week's assignment or like the week's lecture, you can ask, or else we will proceed with today's discussion. I'll just wait here for a couple of minutes. Meanwhile, I will just check if the recording is started or not. Let's go. The recording is done. I see. Okay, the recording is going on. All right. Okay. All right, guys. If you don't have any questions, let us start with today's discussion. So basically, as I said, we are going to solve some more problems on laminar boundary layer theory. Uh, Typically over a flat plate, because flat plate is you can say it's an easier version of going into more complex problems, and the algebra that is associated with flat plate analysis is more or less analytically tractable. So we will proceed with the flat plate, and then we will slowly increase the complexity. So in this question, it's given that the velocity profile, unlike the velocity profile that was not a priori given in the previous question, where we need to evaluate the constants, where we basically use the boundary conditions to evaluate the constants. In this question, the velocity profile is already given to us, which is basically a sinusoidal profile, which is so u by u infinity as a function of y by delta is just this. It's a sinusoidal profile, as you can say. You can verify that the boundary conditions that we use to evaluate the constants ABC in the previous problem essentially satisfies this velocity profile, or the other way around, this velocity profile satisfies the boundary conditions. Okay, how can you say that? Let's check what happens when y basically becomes equal to 0. When y equal to 0, u is 0, so the no slip boundary condition is satisfied. When y becomes equal to delta, u by infinity becomes equal to 1, which means this is also satisfied. And you can also show that when you calculate del u by del y, this will become a cosine function. That means at pi by 2, this function would essentially go to 0. Which means all the three boundary conditions that we saw in the previous exercise or in the previous problem is indeed satisfied by this velocity profile as well. But based on this is not what we are asked to do. So what we are asked is, we are asked to evaluate three things basically. First, we are asked to evaluate the boundary layer thickness delta, and we are asked we are asked basically how does delta basically varies along x. That is something that we are asked to evaluate. And then we are asked also to evaluate the displacement thickness delta star as a function of x. This is the second task that we need to do. And lastly, this is something new with respect to the previous problem, is that they have also asked us to evaluate the drag force on a plate of length L and width V. So what will be the drag force on this plate, provided the velocity profile is given by this. Okay, so these are the three things that we will basically solve for in this equation. So before going into the solution, I hope the the problem is clear to you. So if you have any doubt, you can ask, or else we'll begin with the solution. So let's start solving this problem systematically. So it's given that the velocity profile u by u infinity is nothing but, so it's what? It's just sine of pi by 2 into y by delta. Okay, so this is given to us. Oops, sorry, 1 second. Sorry for the interruption. So I was telling that the velocity profile u by infinity is given to us, okay, which is basically a sinusoidal function, which means so it's so this basically means that this u by u infinity bears the signature of this sine function pi by 2 into y by del, okay, when my y essentially varies from 0 to delta. And we all know that when we move away from the inviscid region or when we move into the when we move away from the viscous region into the inviscid region, we know that u basically is equal to u infinity. So this is 1 when y is greater than delta. Okay, based on this, let's first now, so the first step of evaluating how the displacement thickness, evaluating how the boundary layer thickness varies along x is by calculating the shear stress once we are known with the velocity profile. So the velocity profile tau w, okay, once we know the wall shear stress, I'm very sorry. So once we know the velocity profile, the first step the of calculating how the boundary layer thickness varying along x is by first calculating the wall shear stress, and the wall shear stress tau w is, as we all know, is given by mu times of del u by del y at y equal to 0. Okay, and this is simple to evaluate. So if you evaluate this, what we will get, because at y equal to 0 we know that the velocity profile is this, so our tau w is mu times, it will be what, it will be, it is del u by del y evaluated at y equal to 0. So it will be mu u. So this u infinity will come out because u is basically u infinity times sine of this function. So that's why there will be an u infinity here times the constant will come out. Basically, this pi by 2 delta will come out, and then we will have cos of pi y by 2 delta, and this varies from what? This varies. So sorry, this need to be evaluated at y equal to 0. So as we all know, just 1 second. Yeah. Okay. Yeah. So as we all know, so just to summarize what we are doing, we are basically trying to solve a problem on this laminar boundary layer analysis, where we basically had this velocity profile. So it's a sinusoidal velocity profile, and we just now checked that the boundary conditions, the three boundary conditions at so the no slip boundary condition at y equal to 0, and basically the fact that u is equal to u infinity at y equal to delta, and del u by del y at y equal to delta is equal to 0 at y equal to delta, of course, is 0. So we check that these three boundary conditions are indeed satisfied, and then our first task is to evaluate the how the boundary layer thickness varies along x, and then the subsequent task were to find out the displacement thickness delta star, and then the drag force on a plate which bears a length L with an width B. Okay, so that's what we did. So as I said, the first task of calculating the boundary layer thickness is first, if we are given a velocity profile, is to evaluate the wall shear stress, and the wall shear stress is basically given by this, as we all know. And then if we evaluate this, so what this will be, so at y equal to 0, cos 0 is basically 1, so this will just turn out to be 1, which means my wall shear stress is nothing but u infinity times mu. You can write it as a del. So it becomes u infinity times mu by delta into pi by 2. This is basically our wall shear stress that we got. So once we know the wall shear stress, as we did in the last class, the next, so what we can do, so we can use since so it's so just think of it like that. So we know the velocity profile, and we know the how the wall shear stress is, or we know the magnitude of the wall shear stress. This means the next thing that we can use to evaluate how the boundary layer thickness basically varies along x is by using the momentum integral equation, as we all know. So we will use the momentum integral equation. Okay, so since we already saw this, I will not explain this here much. So the momentum integral equation is nothing but tau w by the flow kinetic energy, basically, uh, which is rho u infinity square is equal to d theta by dx, where we know that this theta is what? So it is nothing but the momentum thickness. Okay. So this theta can be expressed as the velocity profile as something like this. So it is integral 0 to delta u by u infinity into 1 minus of u by u infinity times d1. Okay. So we know what, so we calculated the wall shear stress. So wall shear stress is basically u infinity mu by delta times of pi by 2. Okay. This is what we got from here. And then we have this rho times of u infinity squared. Okay. And this can be written as ddx of integral 0 to delta. It is what? So u by infinity is a sine function this time. So it is sine of pi by 2 into y by delta. Okay. Into 1 minus sine of pi by 2 into y by delta. Okay. Times of dy. All right. So before solving the integral, okay, this is, so we need to solve this integral, but before solving that, let's first simplify this term. So u infinity will be cancelled by this. Okay, which means this term simplifies to what? This term simplifies to uh, 2 delta rho u infinity. This will come into the denominator, and the numerator is nothing but mu times pi, I think. Yeah. Okay. All right. Now let's calculate this integral. And here you need to help me out. So let's do this. Let's calculate this integral. So it's integral 0 to delta sine of pi by 2 into y by delta times 1 minus sine of pi by 2 into y by delta dy. So what is the, so if you remember, what is the first step in evaluating this integral? So what? So we need to make a substitution. So I mean, you can evaluate this integral without the substitution, but there's an easier way for calculating this integral by making a substitution. So can you tell me what's the first step? So what's the first substitution that we need to do here in order to evaluate this integral?
Pi y by 2 delta equal to 0.
Yeah, pi y by. So you are telling that pi y by 2 delta you are taking as some function. That's what you're saying, right? Yeah, that can be done. That can be done. But let's not be bothered about this pi by 2, because pi by 2 is just, it's a mere constant. Okay. So what I will do instead is I can take y by delta as some, let's say, m, as we did in the last class. Uh, all right. So let's do this. And then what do we get? So we get that dy becomes delta times dm, and as I have said, this delta is basically a function of x only. So it will not be bothered about the differentiation in y. So that's why this can be taken out of the differentiation, and that's why this becomes delta times dm. And then if you evaluate this, it will become integral 0 to 1. It is sine times of pi by 2m. Okay, you can take this pi by 2 also inside this. It will just remain as a constant, and after all, it will, when you are done solving the integral, the pi by 2 will just come up. So that's why you can just take y by delta as m. That's the idea. But anyways, so the next term is just 1 minus sine pi by 2m, and dy is delta dm, but I know that delta is just a constant here, so we are just, we are just left to evaluate this integral. Okay. So so this is now an easy integral to evaluate, because you can just write this integral as integral 0 to 1. It is sine pi by 2m dm, okay, minus integral 0 to 1, it is sine square pi by 2m dm. That's all you can do, and then you can just so this integration will become what? So it will become, so there will be this cos term here, and then it will be pi by 2m, and there will be this 2 by pi, which will basically come out, I think. So you can, so the thing is, you can evaluate this integral now, and I have done that for you. So like, we will skip the math here. So if you are, so if you, so basically if you just solve this integral, so you'll just end up getting 2 by pi into 1 minus of pi by 4. Okay, so it's just simple. Just evaluate these two integral. This 2 by 5 factor obviously will come, because if you solve this integral, and then if you just solve this integral, you will get the other factor. You can just do it yourself and just check it out, that you will eventually just get this answer. Okay, so so this means if we just now plug in the values in this equation, what do we get? You get mu times pi divided by 2 delta, what is that, rho u infinity, and this is equal to d delta by dx into this term, which is 2 by pi into 1 minus of pi by 4. So it is something similar that we did in the last class as well. Okay, so what can we do now? So what we can do is, as we know, we will take this 2 delta with this delta, such that we can make this 2 delta into d delta as d of delta squared, and we'll take all other terms in the other side. So if you do that, basically you will just end up getting something like this. You will just end up getting pi nu by 0.137 times u infinity dx. This is just the math that you can just do it and check, basically. Okay. So now, as you know, the next step is basically to integrate this equation, which means at x equals to 0, I have delta to be equals to 0, and at x equal to some x, I have delta varies as delta x, which means you can eventually show that delta square is pi nu x by 0.137 of u infinity. Okay. And which now means that delta by x, if you want to express this, so this is how your delta square basically varies along x. But if you want to express this in terms of the Reynolds number, just like how we did in the last class, you can show that delta by x is nothing but 4.80 by square root of rex. So that's it. That's basically, so that is basically how delta by, so this is a more familiar form of expressing delta, and that's why we just write it in terms of like the Reynolds number and the local distance in the x direction. So if you remember in the last class, if you remember, we saw that if we choose a second order velocity profile, our delta by, we get this similar form. So now you can see that if we go on changing the velocity profile, the only thing that changes is this constant. Okay, this is the only thing that changes. And if we now choose a sinusoidal profile, you see the constant came out to be 4.80. Again, this is very close to the exact solution, which is delta by x is 5 by rex, the one that we get from the Blasius analysis. But this is again a good way of showing that instead of like getting the velocity profile from the Blasius analysis, which is a bit complicated, you can choose your velocity profile, which should essentially satisfy the boundary condition, and then this works for calculating the how basically the momentum thickness varies along the x direction. So that's again the idea. Before proceeding into calculating the next things, I would like to clarify some things here. Like I was thinking about that. So in the last week only, this is the off topic, but I just remembered this now, so I felt like it should be said. So in the last week, So we were just solving this creeping flow, if you remember. Okay. So while we are solving this creeping flow, basically we are trying to calculate these constants a n, b n, c n, and d n. And if you remember, this a n, b n, and the modes that will be present were known from the far field condition, and we were using the we are using basically the boundary conditions on the sphere surface, which is the no slip and the no penetration, to calculate the constants cn's and dn's. Which means, yeah, so in this problem, we had this n equal to 1 and 3 mode, which means we were now left into calculating four constants c1, d1, and c3 and d3 respectively. So in the calculation of the cn's, I said that we use two boundary conditions on the sphere surface, which is the familiar no slip and the no penetration boundary conditions. Let's check where did we do. Where is it? This is there. Okay. Yeah. So we use the no. This is the no penetration boundary condition, and then we also use the no slip boundary condition. In using this, I think you asked that. I think IUC asked that. Can we use the so you said that we can also use the axisymmetric boundary condition. Okay. So I think that's what you asked, right? We can also use the axisymmetric boundary condition. So is that something you said, right? If I'm
Yeah, yeah.
Yeah, so yeah, so that I was actually thinking about that. So here so you have already enforced the fact that your problem is axisymmetry. Okay, so it's basically you are in a spherical space, and you are basically looking into two variables r and theta, and you are not concerned about this phi factor. So as I said, in spherical geometry, axisymmetry means your variables are already independent of phi, and the fact that if the variable is independent of phi, it also implies in the sense of axisymmetry that if you take gradient with respect to phi, that will always be zero. This means this cannot be served as a boundary condition, because this is already incorporated into the axisymmetric assumption that we considered, and that's why we are using the stream function approach. Okay, so we cannot use the axisymmetry because we don't have any variable in terms of phi, right? In terms of phi or in derivatives of phi. That's the first thing. So did you understand why there is no point using the axisymmetric boundary condition here? Because this problem is itself axisymmetric, and that's why we said that if the problem is axisymmetric, we can use the stream function and then can use the series solution, which is basically a series expansion in R times the Eigenvalue polynomials. Okay, so a similar problem you might have done in your lecture classes, where you saw that your solution for psi was something like this. So it was f of r times some, I think it was some, if I'm not wrong, it was some function of basically, I think it was sine square theta or something like this. So your solution was something like this. Okay. So this solution again, as well as the one that we did in this problem, is axisymmetric in nature. So it's inherently satisfied the axisymmetric boundary condition. That's the first thing. So did you understand, like,
Yes, yes.
yeah, so this is the first thing. And the second thing, I also want to point it out that in one of your assignments, I think the assignment on this lubrication theory week, I think it's week 6 or whatever it is. It was asked that for a creeping flow, what is the ratio of the drag induced by the pressure to the viscous drag? Now, here is the thing. So, I said that, so what we did is, we basically calculate this constant C1, D1 and this C3, D3, and I said that we will now use a theorem which says that the drag force is proportional to C1, which means that if you know C1, which means that in order to calculate the drag force, all you require is the constant C1. But this theorem loses its validity if someone asks that what will be the individual contributions of the form drag, that is the drag induced by the pressure, and the viscous drag, because this Fj is basically the total drag. Okay, so if you now ask me that in this problem what is the contribution from the pressure drag and the viscous drag, then I cannot like pinpointedly, or like I cannot segregate it, and I cannot like say this much is the contribution from pressure drag and this much is the contribution from this thing, what to say, the viscous drag. So if you are using the theorem, this will basically give you the total drag, and this is something that we seek actually. But if you are asked to evaluate the pressure drag and the viscous drag individually, then you cannot use this theorem, and then you have to use the more traditional way of evaluating basic. So what then you, so as I said, you have to use the traditional way, which means you need to evaluate the stream function psi, that we already did. From psi you need to evaluate the stress tau r theta. So if you know tau r theta, this is sufficient to give you. So if you integrate, so if you have a sphere and you integrate this tau r theta along this surface, and then you integrate it over the entire sphere, you will basically get the viscous drag. That is something that you saw in your theory classes. And similarly, in order to know the pressure drag, all you need to do is, you know that pressure satisfied what? Pressure satisfies minus gradient of P plus del square V equal to 0. Okay, and you know this velocity field now because you know stream function, which means all you need to calculate is this gradient of pressure. So this means in r direction, this gradient of pressure would be just del P by del R. So this means the pressure drag can also be the pressure can also be individually calculated once you know the stream function. That's the thing. And then you need to individually calculate what is the contribution of the form drag and what is the contribution of the viscous drag. That's the idea. I just wanted to clarify.
Can
Yeah.
we also subtract from total drag viscous drag to get pressure drag?
Yeah, exactly. Because
Uh,
yeah, of course. Because your governing equation is linear, right? So you can do that. You can do that. That you can do. All right. So this is something that I wish to say, and I remember it now. So, but anyways, I hope this is clear. So let's proceed with our analysis of boundary layers. All right. So the second part that the question has been asking us is to calculate the displacement thickness. And we know this displacement thickness is given by delta star. So do you know what basically is meant? So what physically, so there is a mathematical expression for delta star, but what physically is signified? So what physically does displacement thickness signify? Can you give it a try? Like what physically does this quantity mean?
this is the offset by which potential flow is offsetted from surface.
Yeah, exactly, exactly. That's that's exactly what it signifies. In simpler words, what does it mean is, what essentially it means is, if you don't, if you, let's say there is a flow and there is a flat plate, okay, and okay, I'll draw it in a better way. So what you said is absolutely right, but just to simplify what you said, if there is a flow and there is a flat plate and you are using the fact that the flow is inviscid in nature, okay, then if you calculate the mass flow rate, let's say in this region of the plate, it will be some m dot. Okay, let's say this is m dot 1, and remember you are considering the flow to be inviscid. Now in the same sense, you take this similar plate, but use the fact that this time your flow that is coming from the background with some, let's say, u infinity, okay, this is viscous in nature, which means now there will be a development of a boundary layer. Okay, there will now be a development of a boundary layer, and for this definite reason, if you want to, if you want basically to get the same mass flow rate, you need to shift your boundary layer to some more length in order to compensate for the loss of mass flow rate. Okay, and that is typically known as the displacement thickness. So I hope this is clear, and this is exactly what you said. So what you said implies what I basically stated right now. So I hope this is fine, right? You understood that, right?
Yeah.
Yeah, exactly. Okay, so it's like, so as I have said, it's like, so how much your boundary layer thickness need to shift in order to compensate for the loss of mass flow rate when you move from the assumption that your flow is viscous in place of your potential flow theory or your inviscid flow assumption. Okay, so it's just that shift, basically just that shift with which, so it's just the shift with which your boundary layer basically need to consider, I mean, you need to consider in your boundary layer so that you compensate for the loss of mass flow rate, basically. In anyways, can you now tell me what is the expression for delta star, if you remember?
Integral 0 to
Yeah,
delta u by
yeah,
u infinity into 1 minus u by u infinity.
So u by u infinity into 1 minus u by infinity is then momentum thickness. This is displacement thickness, right? So it will be 1 minus
Oh,
u by
sorry,
u.
sorry.
Yeah,
Sorry. Without u by u
yeah,
infinity in there.
yeah,
Right.
exactly, exactly. That's okay, exactly. So this is basically your displacement thickness. And do you know how this displacement thickness is essentially calculated? So it's very simple basically. You just need to apply mass conservation here. Okay, you just need to use RTT and apply mass conservation to get basically the displacement thickness. That's it. But anyways, we'll not go into the derivations here, but we will just evaluate what will be delta star. So if you now evaluate delta star from this, what will you get? So it is integral 0 to delta u by, so it is 1 minus u by infinity sine of pi by 2 times y by delta into this dy. Okay. And then again, we will make the same substitution. We'll do the same exercise, that y by delta will take it as m, which means dy is just m times of d delta. Oops, sorry, it is delta times of dm. Okay. And this means your delta star is, so this will come out to be integral 0 to delta, sorry, integral 0 to 1, delta times integral 0 to 1 minus sine of pi by 2 m, and then this is dm. And then if you calculate what you will get is, you will get something like this. Delta, so you will get is delta star is equal to delta, and if you evaluate this integral, okay, you will get something. So you will get around 1 minus 2 pi basically, because that is simple, right? So the first term here would give you 1. Integration of this would just give you 2 by pi, because this 2 by pi would just come out. Okay. And yeah, so that's it. So that's the displacement thickness basically. So if you now take the ratio of delta star by delta, you will get it to be around 1 minus 2 by pi. And from here also, if they ask you to evaluate the shape factor, you can just do it. I think it's the inverse of this ratio, which is basically the shape factor, if I correctly remember. Okay. All right. So that was simple, the displacement thickness. Now the last part, I hope you are uh, so you are okay with the math here. So all you need to do is just the integrations, which I feel is very simple at this point of time. So the last part is basically to evaluate the drag force. And how do we do here? Can you tell me? Can you give us an idea how do we evaluate the drag force? Remember, we need to evaluate the drag force on a plate of length L and width B. Okay, this means if your plate length is L, okay, and your width is basically B, you need to evaluate the drag force here. This is your L and this is your B. So how do we do that? Can you give it a try?
Shear drag by that mu du by dy.
Yeah, exactly. So exactly. So the thing is, here we need to just think, okay, from where the drag will be induced. Okay, do we have any form of form drag here? I mean, do we have a drag induced by the pressure?
No.
You know, right? Because it's a flat plate theory basically,
Yes,
that
yes.
which means that the only force that can, I mean, the only form of drag that can come into our problem is by the action of these viscous forces. Okay, which means I need to now evaluate basically the wall shear stress. Okay, and then if we now evaluate the wall shear stress, that wall shear stress is sufficient for us to give us that basically the shear drag, as you said. Okay, so now how do we need to so now how do we basically need to do? So what we will do is, first of all, we will evaluate tau w. As so tau w we have already evaluated, right? So I think, what was tau w? Tau w is, hold on, yeah, so tau w is basically, so it is mu times u infinity by delta into pi by 2. Okay, let's write it here. So it is just mu times u infinity by delta into pi by 2. This was tau w. So the idea is, since this delta, so all I am asking is, see, is it sufficient or is the drag force just correct if I just take this tau w and multiply it by L into times B? So is this correct or wrong?
No, no. Delta is
Yeah.
function of
Yeah,
x.
exactly. Yeah, exactly. So which means, although it is not like so, it doesn't appear, but you must always take into the fact that this delta, which is basically your, as you have rightly pointed out, this delta, which is basically your boundary layer thickness, this is always a function of x. Okay, which means when I move along this plate, your wall shear stress essentially varies. Okay, and can you tell me that, so you know that delta basically varies as square root of x. Okay, that is something that you know. So from here you can tell that tau w is basically 1 by, so it varies as 1 upon root over of x, because you know that your delta varies as square root of x and all these things are just constants. Okay, so this means for a flat plate analysis, if your u infinity is not a function of, if it is not a function of x, which is the case in case of a flat plate analysis, you know that since the boundary layer thickness varies as inverse of root over x, sorry, boundary layer thickness varies as root over x, your wall shear stress essentially varies as inverse of root over x, which means you can also show how the wall shear stress profile looks like in this plate. But anyways, the bottom line is that when you move far stream to the far stream of the plate, your wall shear stress essentially decreases with respect to the fact that your wall shear stress is, so it's maximum. So there is a singularity point actually. Okay, at this point there is a singularity point, but apart from the singularity point, so the value of wall shear stress at the point where x equal to 0 is not defined, so it can only be calculated experimentally. But apart from that x equal to 0, let's say at x equal to 0.001 from where the numerics can be done. Okay, I mean numerics means where the algebra can be done. It is the point which bears the maximum shear stress, and from that the shear stress essentially decreases as 1 by root over x, which means what you need to do now is you need to take a strip at any point x. Okay, let's say this, and then in this strip, okay, so the distance of this strip is, let's say, x. Okay, and then in this strip, so why do you take a strip? That is simply because your wall shear stress essentially is a function of x. So you are taking a point in this plate where your wall shear stress can be assumed to be constant, and then you find the area of this strip. So what will be the area? So this thickness is dx, its width is b, which means the elemental area dA of the strip is basically b times dx. Okay, now what you need to do is the elemental drag force, I would say dFd, is, in this case, since you are assuming that in this strip the wall shear stress is assumed to be constant because because the thickness of this strip is infinitesimally very small, then in this case you can write that your drag force is nothing but tau w times b dx. Okay, which is basically the wall shear stress multiplied by the area. And then what you need to do is you need to substitute now the value of tau w, which is what? Which is mu times u infinity by delta into pi by 2 b dx. And then in order to evaluate the drag force, you need to integrate it from 0 to L. You need to integrate this term. Basically, it is pi by 2 b dx. So what you get is, if you take out all the constant outside, which means your pi by 2 is a constant, mu u infinity b is a constant. This means you need to integrate it from 0 to L. It is 1 by delta dx. Okay, and you know what's delta, right? Because we have already evaluated how delta varies along x. Okay, so if you remember now, so we evaluated that delta by x is what? So if you remember, it was 4.80 by square root of Rex. Okay. So this means what you can do is you can write 1 by delta as what? You can write it as square root of Rex by 4.80x, if I'm not wrong. And then you need to substitute this. You need to substitute this into this. Okay. And how did we get this? Because this we just evaluated. This is from part part 1. Okay, so let's do this. Let's do the substitution and then try out. So this means your drag force is what? So it will be pi by 2 into mu u infinity b into integral 0 to L. Okay, it is square root of Rex by 4.80x, okay, into dx. And now what you can do, what you can do is you can write this term as, so it's just the math. You need to expand you need to write the value of Rex, and then if you just take this constant outside, it will be square root of rho u infinity by mu. All I'm doing is I'm just writing Rex as rho u infinity x by mu, and I'm just taking this constant outside along with the term 4.80. This means all you are left now is to just what you have. Basically, you have square root of x by x, which means it just reduces to 1 by root over x. Okay, so it is just 1 by root over x times dx. I hope the math is clear. And if you now calculate this, if you now do this, this is rather straightforward. So if you do this, you will get something like this. So your drag force will be 0.658 rho u infinity squared dl, which is basically the area, by square root of REL. Okay. Okay. Now let's do one thing. This is the answer that we are looking for, but let's do one simple comparison here with our age-old glaciers. Okay, so what we will do is so this is FD, so we'll do is something like this. We'll bring this rho u infinity square here, and this B into L is basically the frontal area. Okay, it is frontal area means it is the area which is exposed to the air, or it is exposed to the flow. Okay, and then this can be written as 0.658 by square root of REL. Okay, can you tell me what is this?
Coefficient of drag.
Yeah, exactly. So this is coefficient of drag, or it's known as the drag
Coefficient
coefficient.
of friction. Yeah, yeah,
Exactly.
yeah.
Actually, this is coefficient of friction, and then if you integrate it, from there you can calculate the drag coefficient, which is basically obtained from the coefficient of friction.
Yes,
Okay.
yes, yes.
So, anyways, if you remember, so it's just so I'm saying this is just a non-dimensional number. Okay, that's all I'm saying. So the thing is, can you remember what was this value? Okay, in the Blasius solution, if you remember. I mean,
0.64
yeah,
by root L.
exactly. It's 0.664 if you remember. Okay.
Yeah,
Again, as you can see that this answer is very, very close to that of last year's solution. So repeatedly, so from these exercises, you can be rest assured that momentum integral produces, the answers of momentum integral always resembles very closely to that of the Blasius solution. That's again the like point I want to express here. But anyways, this is basically so that's something I want to say. But this is where the answer is asked for. You need to just calculate the drag force from this. Uh, all I was saying this again closely. I can say it's very close to Blasius solution. All right. All right. This finishes our first question. Uh, and I think this question is little bit insightful because like it teaches us basically the momentum thickness, the displacement thickness, then to evaluate how basically to evaluate the drag force for a particular flat plate problem, and so on and so forth. So we will see the second problem, but before that, I'll just stop here for some time. If you have any questions on this solution and the things that we did, you can let me know. Meanwhile, I'll just come in just 1 minute. I'll return in just one. All right. Uh, if you have any questions, you can let me know. Or else, like, we'll begin with the next problem. So the next problem is kind of an interesting problem. So what they're asking is, I think you guys have seen the entire solution on this Blasius flat plate problem. Okay, that similarity approach. So the idea is that you write first so you derive the x momentum equation by simplifying it for a flat plate solution, as we will see shortly. So what you then do is you basically, since that's a 2D problem, as I have said, you can now use the stream function. So so what you do is you replace the velocity with the stream function and then solve that stream function problem, considering the fact that you take a similarity variable eta, and then what you get is basically a ODE in eta, which is basically a nonlinear third order ODE. And then it said that you cannot directly go on and solve that ODE because it's nonlinear, and that's why you need to look for numerical solution. And finally you find out how uh, your stream function as well as your velocity fields basically vary along that. And the takeaway is that you calculate what the drag. So what basically you calculate is you calculate how delta varies along x. That's something that you do. You calculate the wall shear stress maybe, then calculate the drag force and the friction coefficient, as you have said, the drag coefficient, the friction coefficient, and so on and so forth. Okay, but so that's the procedure of this Blasius flat plate problem. But in this question, they're not asking the procedure. What they're asking is, in order to solve the Blasius solution, and in order to like know what will be your similarity variable, what you need to do is you need to non-dimensionalize your simplified boundary layer equations. Okay, and in that, if you need to non-dimensionalize, you need to choose characteristic scales. Okay, as you have said, as we have like saw in many instances before. Okay, so the question says that if you need to non-dimensionalize, you also need to non-dimensionalize your parameter, or I mean, you need to non-dimensionalize your variable stream function, because you said that you are replacing your variables u and v in terms of the stream function, which means if your psi is a variable, you need to also have this psi c. Then this question is asking that what is your psi c in case of this Blasius flat plate problem. So that's what they're asking. Okay, so they're asking us what is your characteristic stream function, which means this psi c, as I have not written, but you might have understood that what is your characteristic stream function. That is simply because the why you require, so I think you must have appreciated that why you require this characteristic stream function is that only then you can write your stream function as some, so your dimensional stream function psi can be written as a characteristic stream function times f of eta, where eta is that similarity variable. Okay, for that you need to know what is psi c. All right. So let's get this started. We will do this. But before that, what we will do is we will first start off with the boundary layer momentum equation for a flat plate. Okay. And what is that? Can you tell me? Can you tell me what is the boundary layer equation for a flat plate? It's the momentum equation in the x direction if simplified for a flat plate. Can you tell me?
U du by dx plus v,
Yeah, exactly.
v
U d by
v du by dy
yeah, and then
equal to mu
yeah,
dou square u by dou square v.
yeah, exactly. So it will be mu if there is a row. I brought this row here, so it will become basically the kinetic viscous.
New, new,
Yeah.
new.
Okay. So now what we will do is, in order to evaluate the characteristic stream function, we must first write this equation in terms of stream function. Okay. So how do we do that? So basically that's simple. We know that u is basically what? It is del psi by del y. So this I think we have seen multiple times. And v is nothing but minus del psi by del x. Okay. So this I think we have seen I mean, throughout the course, we are familiar with this stream function. We have seen that in creeping flows. We have seen that in earlier, like when we did sums on the basic definition of fluid dynamics and so on and so forth. So anyways, needless to say that this form of stream function evolves from the fact that the continuity equation is trivially satisfied. I think that you guys know. So what now we will do is we will now incorporate these form of stream functions into these velocities u and v and their derivatives. So what this would be? So this would be del psi by del y, okay, times this would be what? Del x of del u by del x. So this would become del x of del psi by del y. Okay. All right. Next, this v is minus del psi by del x, which means it is minus of del psi by del x. And this becomes del y of del psi by del y. Okay, because there is this u here, and this u is basically your sorry, it's this u. So this u is basically your del psi by del y. All right. And then the right hand side, you can eventually show that your right hand side. So this would be what? This would be this would be del 2 by del y2 into del psi by del y, which means it would be nu times del 3 psi by del y cube. All right. Okay. So now let's simplify this. So if you simplify, it will be del psi by del y times del x. So it is what it is. So del x of del psi by del y is del 2 psi by del x del y. Okay, and this would become del psi by del x times del square psi by del y square, and this is equal to nu times del 3 psi by del y cube. All right. Okay, so this is something that you get if you write the x momentum equation for a flat plate in terms of the string function. If you go in, so if you remember, if you go into the wedge solution, or for instance, if you go into the Faulkner-Scan wave solution, you have to do the same analysis, just like what you do in glaciers. Only thing is that there will be this pressure gradient, because then you will encounter a non-zero pressure gradient in the x direction, written in terms of the velocity, and then again you need to use the stream function. That's the idea. So in a way, the Blasius flat plate solution is a special case of that Faulkner scale solution, or that wave solution, and so on and so forth that you saw. Okay, so that's why we didn't go typically into that typically much into those Faulkner scan solution and so on and so forth. So the idea is, if you know Blasius, you can easily understand Faulkner scan solution. But anyways, all right. So this equation, as you can see, this is in dimensional form. Now you just, so what we now need to do in order to evaluate this characteristic stream function, we need to non-dimensionalize this equation by choosing certain characteristic variables. Okay. So now you need to tell me that what is xc in this problem. So we need to choose a length scale in the x direction. So what is xc? What is the characteristic length scale in the x direction? Can you tell me?
Length of plate.
Yeah, exactly, length of the plane. But is this correct or not?
No,
Yes, this is not correct. This is not correct. In fact, you can show
delta.
that, yeah, you can show that this YC essentially scales as delta. Can you tell me, if you choose YC as also L, what is the problem do you face physically? There is a
Because
very,
boundary layer thickness is smaller
yeah,
than the plate length.
yeah, exactly. That is a result, actually, I would say. It says that, so like what I'm asking is, suppose you are doing a math problem, you are not a mechanical engineer, you are you're a mathematician, and then you said you don't understand much about flows and all those things, and you said that let's now start off by taking the characteristic scales of y also as L. Then you face a problem, actually. The physics doesn't allow you to do so. There is something which is known as the D'Alembert paradox. Do you know what is the D'Alembert paradox?
That net force on drag force on cylinder is zero.
Yes, it's not exactly on a cylinder. The D'Alembert
Okay,
paradox
and
says that. Yeah, exactly. So I'll tell you what basically happens. So if you choose your xc and yc as just L, and then you non-dimensionalize the x momentum equation, basically this. Okay, then what you will see is, you will get, if you non-dimensional, so what I am saying is, you take xc and yc as L and non-dimensionalize this equation. What you will get is, you will get a term. So what you will get is, you will, so hold on, did I make some mistake? Okay, yeah, so what I'm saying is, you will get a term of 1 by REL here, basically. Okay, And then what I am saying is, in the case when Reynolds number is very high, okay, you loses the viscous term. If you so you can do it yourself and try it out. If you choose xc as L and yc as L and you non-dimensionalize this, you will get an 1 upon Reynolds number here, which means if your Reynolds number is very high, or in the sense 1 by Reynolds number is very small, you loses. So the order of magnitude of this term is very small with compared to the order of magnitude of this term. You can try it out and see. And then which means it says that in case of very high speed flows, you lose the viscous effects. But that is not true physically, right? Which means you don't have the viscous effect, means what? You don't experience a drag force, as you have said. It is not just limited to cylinders, it is limited to flat plates as well. This means that experimentally, when you subject a plate in a very high, when you put a plate in a very high speed flow, the plate obviously would experience a drag force. But if you choose XC and LC, your characteristic scale in the y direction as L, you lose that viscous term. So this apparent mismatch between your theory and the experimental results in this D'Alembert paradox, which means you cannot apply potential flow theory in the analysis of boundary layers and high speed flows and so on and so forth. Okay, and that is why, although like I didn't explicitly show here, and that is why there is a correction to the scaling of yc, and then you can say that your yc scales as delta, basically. So is this clear or not? So is this clear?
Yes.
Yeah. Okay. Okay. So now, so yc scales as delta, and you know, so what do you know? So you know that, so remember, this scale is wrong. This scale is wrong. Okay. So your yc should scale as delta, and you know delta scales as L by square root of REL, or in fact, you know that delta by L scales as just 1 by REL. This is from the scaling analysis. Okay. All right. So now, what more do we need? So in this equation, how many variables do we have? We have x, we have dependent variables x and y. We have also psi. This means I also need to choose a characteristic stream function which we are asked to evaluate. Okay. So we will have to evaluate this psi c. That is something that we are asked to do. Okay. So now if we, so the next step, as you know, is to enforce the non-dimensional variable. So my non-dimensional x bar would be just x by L. My non-dimensional y bar is just y by delta, and my non-dimensional psi bar is basically psi by psi c. And this psi c we will evaluate. Okay. So now what? We just need to evaluate this. We just need to substitute this non-dimensional terms, okay, into this equation, and let's see what do we get. So from here, what will we get? So we will get psi c. So what will we get from here? Okay, let's see. So we will get psi c squared by delta squared L, if I'm not wrong. Okay, let's, so I hope you can understand what I'm trying to say. So all you need to do is you just need to substitute this into this equation. So this can be written as psi c by psi bar, which means that psi c would come out, and similarly you need to do the same exercise with x and y, which means you would get psi c square by delta square L, and then what? Then you will get the non-dimensional numbers del psi bar by del y bar. As so this is something that we did repeatedly. So I hope you are well versed now with writing those non-dimensional equations. But anyway, this is del square psi bar by del x bar, del y bar. Okay, this is the first term. The second term, similarly, so the second term will also scale exactly same. It will be psi c square by delta squared L. Okay, that is because this term and this term is the same only. You have del x by del y square, and here you have the two y's along with x. Okay, which means your scale, your characteristic variables would be the same in denominator and numerator with respect to the first term. And then this would be what? This would be del psi bar times, what do we have? Times del x bar into del square psi bar by del y bar square. Okay. All right. So next we have this term. So this term scales as what? It scales as nu times psi c by delta q. Okay. Which means this is nu psi c by delta q. And then we have this term, del square psi bar by del y bar cube. All right. So now what do we need to do in order to evaluate this psi c? Which terms do we need to compare basically?
Left and
Yeah,
right.
exactly. We can just take this or just the this term because this is basically the same. So what I am saying is that the order of psi c square by delta squared L is of the same order of nu psi c by delta q. Okay. Which means what you can do is this delta square and delta would go. This psi c and this psi c would go, which means your psi c essentially scales as nu L by delta. But we know one thing, okay, this is one result, but like you can express it in a more simplified way. What we know is we know that delta by L scales as 1 upon REL, okay? Which means what? Which means that L by delta will scale as root over REL. All right. So let's do this. So then what do we get? We get, I think, yeah, I think this is correct. Okay. Yeah. Hold on. Delta by L is scale. Okay. Did I do a mistake here? Delta by L. Okay. Yeah, I think it's fine. Okay. Okay. So psi c, this can be written as, so this nu times delta by L is just square root of REL. Yeah, it's correct. Okay. Which means psi c scale says nu times. So what is root over REL? Root over REL is what? It is u infinity times L by nu. And this means your characteristic stream function would scale as square root of u infinity L times nu. So this is the characteristic scale of the stream function. Okay, this is something that we are asked to evaluate, and you need to use this characteristic scale of stream function to non-dimensionalize psi. All right. Anyway. Okay, so you need to use this non-dimensional form of psi and then proceed with the similarity variable to basically calculate the Blasius's result and so on and so forth. But I think this is clear. So what is the characteristic stream function that we basically need to take? And as you can see, your characteristic stream function is nu times square root of REL. Okay, so so you can say that your psi c. Okay, your psi c. So since the REL is a dimensionless number, your psi c has the dimension of nu basically that you can figure it out, which means your psi c's dimension is meter square per second. Okay, which is the dimension of kinematic viscosity. But anyway, yeah, that is something that you can also infer. All right, so this is the second problem that basically was asked. All right, I'll stop here again for some time and then maybe we'll solve one or two more problems. Yeah, we have some time, so we'll solve one or two more problems and then okay, we will I mean, we can then stop with boundary layer. All right. Okay. So if this problem is clear, this is again an easy problem, but it's kind of a more practical problem. Okay. So it says that there is water which is basically flowing. So this is the typical order of magnitude of kinematic viscosity of water. It is flowing over a smooth flat plate at the zero angle of incident with velocity around this. The length of the plate is basically this. Okay. So if this is done, what they're asking is to find out so they're asking what is the boundary layer thickness at x equal to 0.154, and then they're asking what is the rate at which, or how does boundary layer thickness essentially vary with x. I mean, they're asking to evaluate d delta by dx. This is something that they're asking to find. So once this is known, you can find it out. And then they're asking the total drag coefficient basically. So they're asking this. This is already known if you do this, and then they're asking what will be the drag coefficient. Okay, how do we do this? Can you tell me? see, in this problem, they didn't ask us like they didn't say you have to use a velocity profile or like, so what
We
options do
can
we have?
assume
Yeah,
we can use Blasius
yeah, exactly.
solutions.
Yeah, you can use Blasius or you can use any of those momentum integral approach. The result more or less will not differ. But since they have not asked to use any of the, like, they have not pinpointedly said you need to use a specific method, you can just use Blasius solution because that is a well-known solution. So which means that your first answer is then very simple. If you use the Blasius's result, okay, then you can directly say that your delta by x is basically 5 by square root of Rex. Okay, this means your delta is 5x by square root of Rex. Okay, this means your delta is 5x by Rex can be written as u infinity x by nu, and then this can be written as square root of nu by u infinity, okay, times root over x basically. And then they're asking us what is delta at x equal to, yeah, they're asking us the delta at x equal to 0.154, which means you need to substitute x equal to 0.1524 here, and then you'll get the answer. So it is square root of nu u infinity, and then this is square root of 0.1524. Okay, so that's basically the answer. Nu is known to us. This nu is given, u infinity is given, which means you can calculate delta. So now since you know this delta, you can also calculate what is d delta by dx. Basically you need to differentiate this, and then you can calculate what is how delta. So what is the basically the slope of delta with respect to x? That's what they're asked. Okay. So now the third part is that they're asking us to calculate the drag coefficient. Okay, they're asking us to calculate the total drag coefficient basically, and then so how do you do this? How do you calculate the drag coefficient? Can you tell me?
We'll find shear stress
Yeah, exactly.
and then we'll
Yeah,
integrate to find.
exactly. That you can do. So hold on. So yes, that you can do actually. Correct. So you know delta, and so this means you know how delta basically varies along x. But for calculating shear stress, you need to know. Okay, so there are two ways of calculating the shear stress. Okay, yes, you need to calculate shear stress. One way is obtaining the expression from shear stress from the Blasius theory. The second way is to have a velocity profile. From that, you need to evaluate shear stress. So we don't have a velocity profile here. We can assume a velocity profile, but that won't be correct now because we have already followed the Blasius approach, which means we now
Um,
need to follow the Blasius solution. Okay, do the Blasius solution, the entire Blasius solution, evaluate psi, the stream function, then evaluate the velocity, then calculate the shear stress, and then we need to like do this basically we need to have that shear stress in order to calculate the drag coefficient, but it's easier to remember. So as you guys know, there is something called
we
CF, which
can,
is, yeah, which is called the
yeah,
skin friction coefficient, which is basically the wall shear stress divided by the flow kinetic energy. Okay, and this, as you say, it is nothing but 0.664 by square root of Rex. Okay, this means, so yeah, this is not a magical result as I have just written here. It doesn't like come from any hypothesis. It's just as a result of the solution of Blasius's problem. That basically is so it's very simple actually. So tau w, we can write it as mu times del u by del y, and you know u because you know psi basically. Okay, and then you calculate tau w, and from tau w you substitute the value of tau w, and then calculate this CF, which come out to be 0.664 by square root of Rex, as as you have also pointed out in the last question. So once this is known, okay, once this is known, the drag coefficient is related to this CF as something like this. So it is like you are averaging CF along this along the plate length basically. So it is 1 upon n integral 0 to L CF dx. This is the definition of the total drag coefficient, and this you can show that this is nothing but 2 times of CF at x equal to L. Okay, this is also one important result that you can think about. And then if you do this, you just need to evaluate CF at x equal to L. You can show that it is nothing but So what this would be? So it is just 2 times of 0.664, and that's why it would be 1.328 times square root of REL. This is basically your this thing, the total drag coefficient. Oops. All right. Again, I don't think you have a question here because this was again a simple. So these kind of questions basically are expected from boundary layer analysis. So they don't expect a very hard question from boundary layer because like it's not worth remembering so much of results here. So like the conceptualities you need to understand, and then the simple solutions of the Blasius and the momentum integral and so on and so forth, like these kind of things that you can expect. All right, so we'll solve. So this is one. So this is the third problem that we did. So we will discuss something which is known as flow separation because this is important, and then we will like end it a day here. I mean, we'll call it a day. So what I am,
One question I
yeah,
have. Yeah.
sure, yeah, go on.
In the previous question, if flow is at particular angle of incidence,
Ha ha.
uh,
Okay.
then we cannot use this approach.
Yeah,
Uh,
exactly. Then you need to use those Faulkner scan solution, that weight solution basically.
Wedge solution.
Yeah,
Okay.
weight solution, that you need to do that if there is an angular approach there. Because the thing is,
Okay.
this we will discuss like in the next part, okay? Like this flow separation and all those things. So yeah, we'll come back. That's a good point. We'll come back to that. That we will discuss it here. So here we have I have just written a statement. You just need to tell me that is this statement true or false. So what I have said that for a flow separation to take place, first of all, before like understanding the statement, is flow separation possible in case of a flat plate analysis? Like, is this true or false? I mean, if I ask you that can flow separation take place in case of a flat plate analysis for a flow of u infinity, for a flow that is coming at some constant u infinity and there is a flat plate. So can flow separation take place there?
No,
Yeah,
it
exactly.
needs
No.
adverse pressure gradient.
Yeah, exactly. Which means it needs adverse pressure gradient. So pressure gradient where? In the cross stream direction or in the axial direction, basically in the flow direction. Flow
Flow
direction. Yeah,
direction.
exactly. So so I'm right. So this again brings me to one more important point, that I'm also writing one more statement that maybe I'll write it down here. Okay. That adverse pressure gradient is a sufficient condition for flow separation basically. Okay. So I write down two statements as you can see. So now you need to tell me which statement is correct and which statement is wrong if you understood like flow separation. So do you know what's an inflection point, by the way?
Yeah, second derivative zero at that one. Then
Yeah, exactly. So the condition of an inflection point is that
concavity of the flow
exactly. This means
changes.
your nature of the velocity profile should change. I mean,
Yeah.
so if there is a concave, it should change to convex basically. So this means, does this, so can you tell me which curve has a flow separation, sorry, which curve has an inflection point? Or maybe I'll draw this, and then maybe I draw what? Maybe I draw this. So can you tell me which two curves, which of these curves has an inflection point? If this is your y and this is your x, and let's say these are my velocity profiles, u1 of y, u2 of y, okay, and this is u3 of y. So can you now tell me which uh, does you so does u1 of y have an inflection point?
No.
It doesn't have. Okay, it
Y-
doesn't have an inflection point, but
Second has.
yeah, exactly. Does it have u2? It
Yes,
has,
yes.
right? Because it changes. So at this point, you can easily say that the second derivative, that means the slope is zero. It's like it's like del y. Sorry, it's like del y of del u del y is basically zero there. Okay. Does this curve have an inflection point?
Is that turning smooth at that, I mean,
Yes,
from
exactly.
zero?
That's what you need to say. So if there is a smooth
Then,
turn, yeah, then it has an inflection point. But a discontinuity doesn't mean an inflection point. That's what I want to say. So this is not an inflection point. Okay, this is not an inflection point. This is a discontinuous function basically. So
yeah.
it's like at the inflection point, your slope has to be defined basically. If your slope is not defined, then basically that's not the definition of an inflection point. So that's what I want to say. But nevertheless, that is something. So that's then idea on inflection point. But my question was not that. My question is that which of these statements are true and which of these are false. That's the idea. So all I'm asking is, yes, I have an adverse pressure gradient, and I agree that adverse pressure gradient can cause flow separation. But is the condition that so? What is the condition for adverse pressure gradient? Is del P by del X greater than
Adverse
zero?
pressure gradient should be a necessary condition.
Yes, it's a necessary
And
condition, but it's not a
and
sufficient
in
condition.
yeah, inflection point is a sufficient
Yeah,
condition.
exactly, exactly. That is a very good analysis, and you are absolutely correct. Which means this is this is true. This statement is true, and this statement is false. Okay. It is false because this should be the necessary condition in place of a sufficient condition. Okay, that is simple. See, you can have an adverse pressure gradient, but if your adverse pressure gradient is very weak, then you may not have an flow separation, or your flow may not separate. Okay, in the other case, or in the other sense, your velo so it's like so so it's like you are witnessing a flow. Okay, you are witnessing a flow along this wedge basically, which is now not flat, and it is basically curved. And here in that sense, you can have an adverse pressure gradient. So can you tell me in which region of this wedge does flow separation take place? I mean, does it take place here or does it take place here? Yeah,
Downstream.
exactly. So it takes place in the wake region basically. Okay, so if so all I'm saying that if your wedge is not like so it's not like so curved, and you can have a wedge something like this, okay, which is more or less very similar to that of a flat plate. Here also you might have an adverse pressure gradient, but the magnitude of adverse pressure gradient on that wedge would be very very less, which means that your velocity profile, so yes, it's obviously your velocity will tire out as you move downstream, but this will not cause the velocity profile to have to basically flow in the other to basically move in the other direction. Okay, so inflection points means what? After the inflection point, your velocity would be moving in the other direction, and then it will just basically move in this direction. So this is how your velocity profile will look like. So what I am trying to say is a flow separation is caused by the adverse pressure gradient, but adverse pressure gradient is not, so it's necessary, but it is not sufficient to like completely be sure that there will be flow separation. So what more is sufficient is that, so mathematically what you need to see is if your velocity profile that you are given or that you measure. So how do people do this? So basically what they do is they put anemometers in wind tunnels, okay, and that anemometers will basically give you the velocity profile. So then for various objects they try to understand how the velocity profile should look like, and for each and every velocity profile then you can basically calculate if that particular velocity profile does have an inflection point or not. If that have an inflection point, that means you're sure that your flow has been separated. But the other way around, that if you are just putting an adverse pressure gradient and then there is a flow over, let's say, curved surface, or let's say if there is an adverse pressure gradient alone, this may not be the necessary condition. It may not be the sufficient condition to ensure that there will be a flow separation. All right. So that is something that I want to point out. But
One
yeah,
doubt I am having.
yeah. Go
This
on.
separated flow sufficient condition means that
Yeah.
velocity should have an inflection point.
Yeah, exactly. Yes.
And like this question is like from stability point of view. Uh, that stability also one theorem is there that if velocity profile has an inflection point, flow
Yeah.
can become
Yeah, yeah.
unstable. So it's like
Yeah, yeah,
separate.
yeah.
This will
Yes.
be
This may be a constant. So I understand what you're saying. There is a theorem which is known as the Jortov's theorem, basically. sorry, not Jordan, it's the Rayleigh stability theorem.
Rayleigh
Yeah, Rayleigh
stability.
stability analysis. Yeah. So the Rayleigh theorem says that. So it says that. So I think it's the other way around. So anyways, when we will study, maybe in the next class we will study.
I mean, like, will that separated flow will show some oscillations that uh, is
So
it?
that I'm not sure actually. I'm not so frankly I'm not an expert of flow separation, but like it's a good question to think about, but I'm not sure. So I'll try to like think about it. But I don't know what will basically happen to the separated flow. So you understand that there will be some eddies that will be formed. Okay, if the flow
Yeah,
if
like wake or like flow behind cylinder kind of.
yeah, 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 but is this an instability problem? That I don't know, because see, if it's an so instability says that if your flow is, so what that Rayleigh stability theorem says. So if I am not mistaken, it says that if your flow have an uh if your if so it says that if the velocity profile is an inflection point, then there is guaranteed that it's a instability, right? That's so it's
Yeah,
not a
yeah,
sufficient, it's a necessary condition of instability, right? That's what the Rayleigh
yes,
stability equation said. This means that,
yes.
so what happens when there is instability is that the disturbances will now grow in time. By the way, that is very so the instability analysis that you do there, that they are typically known as linear stability analysis. Okay, first of all, you do that linear stability analysis, and these theorems are always very valid for that linear stability analysis, which means, so the consequence of linear stability analysis is that uh, you linearize, so the governing equation for disturbances, you linearize that, then only you can find basically the, so there is something which is known as the Orr-Sommerfeld equation, and so long as, and something like that. So the idea is that is valid for a linear stable analysis, but I don't know that is boundary layer. So is the instabilities that you see, if it arises so in a boundary layer, follow that linear stability analysis, or can you do a linear stability analysis here? That I don't know. But anyway, I will ask. So this is, so I actually don't work on flow stabilities. So I have to study on that, and maybe like if I get some answer, I can come back to you. I mean, maybe I can ask
Okay.
my professors, or like, but I can surely come back to you on that. But do you work? So do you work on these things like?
Okay,
I mean,
not on boundary layer stability.
okay. But anyway, it's a good question. It's a good question. Fine. All right. So yeah. So that's something that I wish to discuss now. Yeah. So we will end this. So we are just about time. So we'll end this. So we'll end this by discussing one more like fact, or one more thing, that in a case, okay, where there is no, sorry, where there is this adverse, where there is the fact that your far field velocity is now a function of x. Okay, let's say there is a flow over this wedge. So let's say there is a wedge. In this case, your u infinity will become a function of x. Okay, and let's say you are taking your u, so there is this thing called like potential flow theory, where from you can take that your u infinity would be of the form some c x to the power m. Okay, and in this case, as you see, because your u infinity is a function of x, you cannot say that dp by dx is 0. And in fact, your dp by dx would be non-zero here. If you apply Bernoulli's equation above the above the viscous layer, you can show that dp by dx. So what basically you can do? So if you apply Bernoulli's equation, because you know that in the inviscid region you can apply Bernoulli's. So if you apply Bernoulli's equation there, you can show that, in fact, it's not Bernoulli. If you apply the Euler's equation also, Bernoulli's or the Euler's equation, the principle is the same. You can show that your u times du by dx is basically nothing but minus dp by dx. Let's say I'm doing it non-dimensionally, which means that if your u is a function of x, okay, which means if your u is a function of x, if this u is a function of x, this means your dp dx is not so this dp dx is not 0. In fact, this dp dx, essentially this dp dx is also very sensitive to the sign of this u infinity. I mean, it's not the sign, it's like it's very sensitive to the profile of this u infinity x. Okay, that's what I want to say. So this means all I want to say is this dp dx now will not be equal to 0. In fact, it will be non-zero, and this would be a function of x. Okay, and in this case, in this scenario, there may be instances, okay, where flow separation can take place, and then these things, so it's the case of that Faulkner scan solutions where you do this kind of analysis. So the necessary condition, so it's like it's one of, so it's like one more necessary condition that you can think of so as to have a flow separation is that your u infinity, which is your far field velocity, if that u infinity is a function of x, okay, then also you can have instances where like there can be flow separation provided your this dp dx is greater than 0. There won't be flow separation if this is less than 0, but like there can be like instances on that. Okay, so with this, I mean, this much should be sufficient for you to understand flow separation. Uh, so with this, we will end boundary layer theories. I think these discussions are sufficient for you to like solve the assignment problems and for the problems in the exam. So we'll end the boundary layer theory here. So in the next class, we will start off with something which with a very important topic. This is known as hydrodynamics instabilities or hydrodynamic stabilities, in whatever way you say. And there, let's see, by the interest of time, let's see how far we can go. But we will do some very good analysis. As you have said today, there is one theorem which is known as the Rayleigh's theorem, which you said now is known as the Rayleigh stability theorem. There is one, there is couple of more theorems. There is something known as the Jortov's criteria. There is something known as the Howard semicircle theorem. So all those theorems in instabilities say that whether a base flow that, so you guys must be aware of the term base flow. So do you know what a base flow means?
over which we give perturbation.
Yeah, exactly. So where basically, so it's like your base flow.
Equilibrium flow, yeah.
Exactly. So your base law essentially satisfies the governing equation. With the help of your base flow, you calculate what will be the governing equations for the perturbations. Okay. And and yeah, so basically that's these things. So there is also something which is known as a Howard semicircle theorem. Okay. So all these theorems says that for a given base flow, like if that is stable or not, if you add perturbation, will that be stable or not? All these theorems are very powerful to say, to predict whether if there is an instability, whether that instability will grow with time or it will decay with time, and things like that. Okay, so we will. So it's a long. Maybe it may be like it may happen that we cannot finish that in a single week, but let's say we'll try to finish it within the next week or the next to next week. And then I think like we will have one or two classes more, and then we'll go into some turbulence concept, and at the last class we will have a summary of all what we saw, and that's all we'll be doing. Okay, so like if you don't have any questions, so we can yeah, yeah, go on.
That flow at an angle of incident you told, you will elaborate.
Yeah, okay. Yeah, so actually what I what I was trying to say is that yeah, that's that's a good point. So what I was trying to say is that so if there is, let's say, let's pick this thing. Okay, let's do this. So let's say you are, so here uh, as you can see here, this wedge angle is, let's say you are defining this wedge angle by some beta. Okay, which means in this case there will be a flow. Okay, there will be a flow. I mean there would be a case where your u infinity is will basically be a function of x, as I have said. Okay, but I'm just thinking that how do you basically, no, I'm just thinking that can you come up with so the thing is, you can, as you know, you can relate this beta with this m. Okay, so so it's like depending on the sign of m, you can have something like this. Okay, you can have, so this is maybe a point. So I don't know the name. They give some name here. So this is maybe one kind of profile. Then depending on this angle beta, if your beta is basically obtuse, you can have this. Okay, so it all depends on this beta, and you can relate this beta to m. Okay, this flow, this wedge angle, this wedge angle beta is related to m. Okay, and there is, I actually don't have, so I had some previous notes so where I actually related this beta with m, and in what cases the pressure gradient would be an adverse pressure gradient. I'll do one thing before starting next, but I just cannot recollect how this beta or m is basically related to the adverse pressure gradient, which can cause a flow separation. Okay, there is a relation basically. So what I will do is I will try to bring it like before starting stability analysis. I'll try to bring this up in the next class, and then I think your doubts will be clarified more on that. I think that would be a better option rather than me blindly throwing arrows. I think it would be good like if I just read that first, and then I will let you know in the next class, like how this beta actually influences. Beta or m is the same thing. You can eventually relate this beta and m, okay, with basically how a flow gets separated and so on and so forth. Is that fine? I mean,
Yeah, yeah, sure.
yeah, sure. Okay, so if no other questions, so we'll stop it for this week. We'll meet next week, hopefully. I mean, we'll meet next week at the same time, and we'll discuss more on this, and then we'll start off with stability analysis. I mean, thank you for joining. Uh, we will end this session now. So I'm ending this meeting. Thank you.